Good morning, everybody. So we start this sixth day of the Escape Summer School. And today, this morning, we have Karl Kozak, who is a researcher at CEA in Paris, France, architect of the CTA pipe software, which is the event reconstruction software for CTA, who will present and talk about debugging and profiling and then optimization. So Karl, the floor is yours.
Thanks. Right, can everybody hear me? It sounds fine?
We can hear you.
Great, okay. So let me just, first I want to just mention a bit about myself. So Tom already just said a bit. So I'm an astrophysicist, so I'm not a computer scientist or anything like that. And I work on high energy astrophysics, so particularly with big shrink-off telescopes like HESS shown in the picture here. And also with CTA, which is the upcoming future large shrink-off telescope being constructed. And my background, other than gamma ray astrophysics, is a little bit in computational physics, which I did when I was my undergrad degree. Also with data analysis, processing, and statistics, and lots of basically scientific software development over the years. So, and one thing I would point out is that I was a really hardcore C++, and Perl programmer up until about maybe, I don't know, 6 or 7 years ago. And then now I would say I work on basically 100% Python. I realize that sounds, actually, now that I read this, it sounds like a 12-step program or something like that. Like, I used to be C, now I'm fully Python. But I think part of the reason for that was that really because of the big ecosystem of scientific libraries and users that we've basically discussed over the past week. So it's not that Python is somehow a magical, perfect language, and that it's the best thing ever. And that's something we'll actually talk about in the next few lectures, about some of the pitfalls of Python and why it's particular speed and things like that. But in this lecture, today at least, we're going to talk about 4 topics. So 2 in the morning and 2 after the break. The first topic is debugging. So I'll talk a bit about what happens when a program runs, what is a debugger, how you use a debugger in various ways you could use one. Then we'll talk about profiling and why you might want to profile your code, what profiling is, and various ways you can use to profile and the speed and the memory usage of your code. And then after the coffee break, we'll start with 2 other more advanced topics. So once you have code that is debugged and you know where the slow parts are, what do you do? So how do you optimize the code? And I'll show just a few strategies for that. There are many actually, but I focus on a few simple ones. And then also about parallelizing your code. So how to run your code efficiently using, let's say, more than one machine, or a machine with more than one core on it. So let's first start out with debugging. So this is a topic that I actually presented at a similar school a couple of years ago. And in the beginning of that, I did a survey, and I was surprised to find that most people actually, never even heard of or they heard of a debugger, but never touched one before. And so the question I want you to ask yourself, it's hard to, with the current setup right now, to have raising hands and things like that. But when you run a piece of code and you get some problem, like you get a crash, an error, an exception happens, or you get a result that isn't what you expected. So you get, not a number, or you get, some crazy answer that isn't what you expected. Or you just want to know what's actually happening when you run the code, under the hood, what's the code actually doing? Is your first instinct to add a bunch of print statements? And that's I think what most people probably do. If you think, deep inside your heart, this is probably what you do most of the time. I even still do it occasionally. It's not a bad thing to do. But of course, that adds, kind of pollution to your code, and you have to remember to remove them later on. And as soon as you've added 3 print statements, you realize there's a place you missed and you should have added another one because you still don't know what's happening. Another strategy people use is to use an interactive Python interpreter, so like IPython, which you saw presented, I think, and Jupyter Notebook, which were both presented in the previous week. Another strategy is to write a set of unit tests and try to narrow down the problem by writing tests for it. I think that's a very good strategy, and you also saw that, I think, presented by Max last week. But one of the strategies I think that is most important is just to first run the code in the debugger, and you'll see that this makes your life much easier once you learn how to do it. It's a little bit tricky in the beginning to learn, but once you've learned it, it's a very useful tool. So the first thing I want to say is how a program works. So this is something that is probably maybe too fundamental for most of you, but it's something that you might not think about so often. So typically what you have is, in memory, you have some program. It has some functions. Functions can call other functions. And what I'm going to show you are three other concepts here. The contents of memory, so what's actually in memory at a given time. And I divided that into global memory, meaning in local memory. This is slightly...
Carl?
Yes?
Sorry for interrupting. We still see your first slide. Is it normal?
No, I've been changing them. Okay.
We are stuck in the first one.
Let me try re-sharing the screen and see if that helps.
Yeah.
Sorry, I'm already on like slide 5. Let's see. Let me try to share screen again. Which do you see right now? Let me just make this full.
We see the slides with the summary on the left.
Full screen. Do you see?
Yes, full screen. Yeah, now it's
okay. Okay, yeah, sorry, that was probably confusing if you didn't actually see what I was seeing on the screen. So where were we? So let's go back to, so here is my question about, what happens when you have a crash or an exception? What do you do? And so, okay, I said, most people add a bunch of print statements and you should run the code in the debugger. So that's to catch up. The slide that was on was here. Yeah, so this was the discussion about how programs run. So on the left here, what I've shown is an example of a really simplistic, this is just a dumb program that does some computation, but has two functions and kind of a main block like you might have in a Python program. And I also show on the right here the contents of the global memory. So that's basically things defined in the main block or shared between all of them, and local memory, which right now there's nothing. Well, I basically count all of this as global memory here. And in the center here, I have something called the call stack. And that will become an important concept as we talk about debugging. And then I have this arrow here saying we are here. This is the current line that is being executed of the code. So imagine we just executed this first line of code. And we define this rad to deg. I just realized that should be deg to rad probably, but anyway, this is a dummy piece of code anyway. And function and or let's say variable, and you see that variable is now in memory. As we then advance the code to the next line, now it's loaded another variable into memory, this dummy variable II that I've put in here for my range. Then we go and we call a function A, using II. And what happens is, of course, we jump into that function. So we're in function A now. So we're now here. And what you see here is that there is this concept of the call stack has now changed, that we were in the main program, now we're in the main program, and on top of that, we're in function A. Function A now in this line calls function B. So what happens if we advance to the next step? Now the call stack has three things on top of it. It's called a stack because you're really putting things on top of one another. And the one that's on top is what's actually currently in local memory. And you can see as we go through these, now the local memory is the variables defined in function B. Global memory is still accessible. Now we go into the next line, function B, so we return a value. And when we return, we jump back one level down the stack. So we are in function B, now the stack goes down to function A. We popped the B function off the top. Now local memory just has the local variables of function A. And then when that returns, we're back to the main program again. And then, of course, we'd go back up to the next step of the loop, and that whole thing would go again. So if I just go back through that, you see that as you go deeper into nesting of calling functions, this call stack gets higher and higher, and then drops down as you get back to the outermost part of your program. So that whole concept is, how programs in this type of interpreted code execute, and it's very important for how debuggers work. So just to put a little bit more technical detail into that, in languages like C and C++, you actually have a distinguishment between the type of memory that's very similar to what was shown there, where you have kind of global memory, which is called the heap. It's also where you put dynamically allocated memory, but that's something very C specific that you don't really think about much in Python. And then you have this stack, and the stack contains the executing function, all of the function in that function's local variables. And all that, the memory that contains that information is called a stack frame. So those boxes in that previous diagram were called stack frames. So you might hear that talked before, and frames are stacked on top of each other to represent a hierarchy, where the bottom is the outermost. So this is exactly what we just saw. The way Python actually works for memory management is a little bit different than this, but the abstraction basically is the same. So you have, you might have a lower level program, you call a function, you go into the first, you create another stack frame on top of it that contains the function plus local variables. It calls another function, those functions return. You might call another function, return again, and go back to the beginning. So stack frames use memory and include all the local variables that are within them. So if you go too deep and you have too many function calls, the functions calling function, you can get what's called a stack overflow. So you probably have heard that term before if you use the internet to search for code questions. That's what the website Stack Overflow is named after. That this error when you actually use too many stack frames and you basically blow up memory and crash your system. Python actually has a built-in stack size limit to prevent you from crashing anything, but and you can get this by typing sys.get recursion limit. So you have to import sys first. And on my machine, at least, I think this is probably language default, but maybe it changes between architectures, I'm not sure, is about 3,000. That means you can call 3,000 functions that call another function. You can go 3,000 levels deep, so your stack can be 3,000 size. And actually, that seems like a large number generally, but if you've ever programmed in let's say, other languages, so C and C++ don't have a limit on this, it's just memory is your own limit on it. And you often write code that's recursive, meaning a function calls itself, and then you can go quite deep into one of these loops of functions calling each other. In Python, you actually can't. So in Python, you do hit this limit at some point. You can change the limit. You can actually set the recursion limit to a higher value if you really need it. But in general, it's not very great for very deep recursive problems, but it's something to remember. And what happens when you hit this limit is you get a recursion error exception that's raised, and that'll come up in a future demo slide. So now, after explaining all of that, what is a debugger? So a debugger is just a program that attaches to a running piece of code. So it can be a Python code, it could be C, doesn't matter, or one that just crashed and had some sort of exception thrown. And it allows you to then inspect that code and view the value of any variable in the code. And so if it's a crash, you basically only get to view the variables that were last assigned, let's say. However, if the program is still running and you'll see in a moment, moving through the program, you have the option of looking at any variable and also seeing how those variables change over time. It also allows you to move through the execution of the code under your own control and inspect what data is there. So you can go to the next line, for instance. You can step into a function. You can step over a function to not go deep inside it. You can look up and down the call stack, basically go up in one level or down one level of function calls. You can say, wait until a variable changes to a particular value and then make an alert. And then you can also say, keep running until some condition occurs, like you get to a line that you find interesting or that a value changes to some value that you want to check. And the basic concepts of debugging that I'm going to talk about here are really independent of language. So we're going to be talking about the Python debugger, of course, because that's the kind of the language we're using in this course. But if you use the C++ debugger or C debugger or Java debugger, they all work almost identically with almost the same commands. So once you learn one, you can use all of them. So there's two levels of debugging interface. There's text mode debuggers. So this is basically the PDB, which is what we're going to be using today, and GDB for C++. That's the GNU debugger. This is the Python debugger. These provide a simple command line interface with text commands, kind of like a shell kind of thing, and they're good for quick debugging, but it's a little bit harder, conceptually to use. But that's the first thing we'll show. But then there are also GUI debuggers, which have nice interactive elements to them, and they're often integrated into your IDE, your integrated development, or interactive development environment, which is, so if you use PyCharm or VS Code or Emacs with lots of plugins included, you probably already have some level of GUI debugging built in. And they allow you to do like point and click inspection of code. You can put your mouse over a variable, see the value of it. So some examples, as I just said, are the PyCharm, VS Code, Emacs debuggers. There is also GNU DDD. This is actually not a Python debugger, but it's one I like to show because it's one that's very, very nice done. It's been around for a long time. And it even lets you show things like the graphical view of your variables and how they relate to each other and things like that. So there's some very fancy advanced debugging systems out there. So in Python code, there are many ways to enter the debugger. So the most common use case, I think, is debugging after an exception has happened, because that's at least what I do all the time. So I run a program, and by the way, I think you learned about IPython in the previous lectures. So I actually highly recommend always using IPython and not Python, the executable itself, because IPython provides you a lot of extra features, and one of them is being able to debug on a crash. So if the program crashes with an exception in IPython, you can just type %debug, and it'll pop into a debugging interface. You can also run it explicitly in a debugger this way. Excuse me. And then the interface has these following commands. I'm going to demo this in a moment, so you don't have to remember these, but you can go up and down the stack. You can show a backtrace, which shows you the entire stack at once. You can continue running the program until something happens. You can go to the next line. You can step into the next function. You can list what code is at the current point, and you can quit at the end. You can also type any Python expression at any time. So you can inspect a variable by printing it out or calling one of its functions. So there'll be a demo of that in just a second. But just to be complete here, there's also another case where no exception occurred, but you want to see what's happening inside a function. So the brute force way of jumping into a debugger in modern versions of Python, so if you're using Python 3.7 and above, there's a slightly different syntax if you're using an older version. It's just to put the word breakpoint with the function call anywhere inside your program, and wherever it hits that breakpoint, it'll jump into the debugger. So that's actually quite easy. So it's better than putting print statements, because then once you're in here, you can view all the variables, not just printing out the one that you thought of at the time. And then there's another way, like similar to what I showed before, that you can run Python with the PDB module and run your script that way, and then it will start up the entire script inside the debugger. And then you can, so nothing will be, you don't have to wait for a crash there. You can just step through your code and run it as you would. So I think that's the good time to do a demo. I just want to put one tip here that I think, I don't know if well, there's two things. You can control which debugger runs actually by setting the Python breakpoint environment variable. So by default, it's PDB, which is the Python debugger, the default one that's built in. I actually quite like this IPDB, which is basically like IPython debugger. It's slightly nicer. You might have to install it. I don't remember if it's in our current install right now or not. But this is a way you can change which debugger, and you basically tell it which function to run when the breakpoint happens. So here it would be IPDB set trace. And then when you run Python my script and you have a breakpoint in there, it will start this debugger instead of PDB. So another thing to mention is that I think you covered unit tests in last week. I can't remember which day it was, on Thursday, I think. If your unit test fails, then you can also have the unit test system PyTest automatically jump into the debugger when the test fails. And that's super useful. I use this all the time. So you just put --PDB when you run PyTest. And you can have any other options after that. Or you can say, even if the test doesn't fail, run all tests in the debugger by running --trace. So this will become more obvious in a second. So let's look at an example first. So first of all, let me open up my debugging notebook. Do you see my screen here? Hope it's switched properly. I guess so. So this is a little example I made just for playing with some debugging. So it's not a very exciting program, but this is a program that computes the golden mean by using Fibonacci numbers. So it's not the best way to compute the golden mean, but it takes the the two Fibonacci numbers, the next two Fibonacci numbers divides them, and that number should approach the golden mean. So it's a very simple program. So there's a couple bugs in it. And one thing I wanted to also point out is that those debugging commands that I talked about for IPython also work in the notebook, and you'll see in a second how that works. So, okay, here's this program. First of all, it computes the Fibonacci numbers recursively. Then I have a function to compute the golden ratio by taking a Fibonacci number, its previous one, and dividing them. And then we plot that for a series of values, and we see how it approaches the golden mean. So let's run it. And okay, and you'll see there were bugs, so it crashed, right? So this is the kind of typical thing you see when you have a problem in your code. And we see, okay, we got a recursion error. So this is the maximum recursion depth exceeded in comparison. Let's jump into the debugger just to see what's happening. We probably know here what's happening, but so let's make a cell, and if I just type %debug and enter, now we're in this debugging interface, and you see we're actually in the Fibonacci function right now. So we're not, normally you wouldn't be able to access variables in these functions because they're already defined, but I'm here inside the Fibonacci function. I can type k, and you'll see I can see the value of k. If I type question mark, I get help. These are all the debugging commands that I can type. These ones I mentioned before. There's more as well. So like list, long list, backwards, forwards. I see Max is mentioning that sticking with Fibonacci numbers was a good idea. Actually, I didn't realize you also did that as a demo, but that's good. It's good to be consistent. Okay, so here I am. Again, I have a problem here that this number looks fine. Okay, k looks okay. So what's the problem? So let's go up the stack. So if I type up or just u, it says now I'm at one level higher. What is k? It's 3. I go up the stack, I type k, it's 2. Okay, so my code does seem to be doing something. The k is changing of time. I can go down the stack again, back to where I was, and go down, down. But of course here, if I kept going up, I'd realize that I can go up basically forever because I've hit the stack recursion limit. So my problem really is that I've called a function that's gone on forever. So let's type q to quit the debugger. We look back up at our code and we say, okay, that's clearly a problem with the recursive step here. And I see that, okay, wait, the Fibonacci sequence is k minus 2 plus k minus 1. I put a plus here. So let's put the minus in there. And that should fix it, right? No. So now I have another bug, right? And I see it says x and y must be the same size. So because I had a plot here. Okay, you might be able to figure this out. This is a very contrived example from the value error. But let's say I didn't know what was going on here. And also I look at this trace back and this is the stack, by the way, you're seeing here. And it's clearly happening somewhere inside matplotlib, the axis.py. In a real case, this might be happening somewhere in one of your library codes or somebody else's code. And it's hard to tell. So let's go into the stack, run debug. Let's make sure I'm not too far off here. So here we are at some line 4498 of this axes.py package. And I can actually inspect what variables are in this line. By the way, if you want a longer listing, you type LL and it should give you more context. So this is the entire function. And the arrow is this "you are here" arrow. So this is where we are in the code right now. So let's see here. So I'm getting a lot of Slack messages for some reason, but I think my Slack is turned off. So let me just quit Slack just so I don't hear that in the background. Okay, so we are here at this raised value error, and x and y size must be the same. Well, let's just print out what x and y are. So x is this array, and y is that array there. So these are this was my input and it's the x axis of my plot, and this was the values I wanted to plot. Again, where were we? We were at this line. If we go up the stack once, let me go back down again. So first of all, we were here in this function called axes.py, or there was a function within axes.py. We go up the stack. Now we're in the calling function that called that. So this is something also I don't know what it is. It says return func of ax and all these information. I can check what these things are by typing typing their variables, and that's a subplot. Data is nothing, it looks like. So that's why this is being called data is none. I can go up the stack again, and I can see, here, now I'm in my code. So I'm in my plot.scatter command, and I was plotting range of max k versus ratios. And if I look at ratios, let's do len of ratios. There's 23 elements, and I can say len of range max k. There's 25 elements. So here's my problem. So I'm plotting at the wrong x and y. So I probably could have guessed that, of course, from this error message, but in a real case, you might be very confused by what it is. So here I've been able to explore up and down, not just drill down into the matplotlib code, but I'm able to go up to my code to see where it's actually failing. So now, okay, I'll quit that and I'll fix my bug. Now, unfortunately, this debugger running it in the cell here keeps all this output, which is quite a lot. I'm just going to cut it away so we don't see it. So then here I'd say, okay, what I forgot here is that I really should go from, I created the data in 2 to max, and I plotted from 0 to max. So I really should have run 2 to max. And then my plot works. So now I plotted, the value of the golden ratio, and this is the golden ratio divided by the actual golden ratio, or minus the actual golden ratio. And you can see it approaches 0. So the difference approaches 0. So that was nice. So that was an easy function to compute. By the way, we're going to come back to this function in the optimization section. So that's why, one of the reasons why I introduced this as well. So it's debugged now, but we're going to come back to it. So another thing is debugging a script after it is executed, but in the terminal. So let me just show you how that works. So here is a terminal here. I think you can see it. Actually, no, do I have the terminal open with, yeah, I think this is the escape school. Do you see my screen now? I hope so. I don't have any responses, so I have no idea what's happening.
You can see your terminal.
Good. So here's a terminal. Let me just close. This is just the same directory from the escape school. And I made a few little functions here to try debugging. So there's another piece of code here called debug Fermi. And this is a piece of code that does something that you might do as an astronomer. So it gets some data from a catalog using AstroPy, so it calls table.read. And then it makes a plot of some columns in that data. So it plots here the spatial distribution of the objects in this catalog, and it color codes them by some value, right? So it's a fairly simple program, but the kind of thing you might actually do. So I plot here, it gets the data, converts the data to raw dec from galactic coordinates, and then plots them, to galactic coordinates from raw dec, and it plots them with the variability index, so the spectral index as a color code. And the catalog I'm using is the Fermi high energy catalog of sources from the Fermi Space Telescope. So that's something you might actually use. And again, let's try debugging this. If I type, first of all, there's 2 things I want to do. This is a code that I want to run interactively. So I'm going to run it in IPython. And I'm going to actually use a couple options here, -I, which means stay interactive after the program has finished ending, and matplotlib equals auto. And I actually don't know why these aren't the defaults for IPython. If you use IPython, you should always use this sequence to run IPython. Don't run IPython on its own. This is really the killer way to run it. I don't even understand why you'd run it in another way. So what I often do is do like alias II or something like that equals that. Now I can just type II debug fib. Oh, by the way, the reason why I do that, just as a side note, if this hasn't been presented before, now if I run IPython with this options, -I matplotlib equals auto, and I open a plot like import .py plot as plot, and I do plots dot, actually, let me just, before I just don't have to type everything here, let me just do a import everything. So let's say I want to do plot a range 10. Now I've popped up a window with my plot, but the window is running in a separate thread because I told it that is one of the options. And if I, let me make this smaller, if I do now plot select title test, it automatically updates there. I can plot, let's say sine, a range, 100, I don't know, on top of that, and the plot keeps updating. So having interactive use of your plots is very important, and being able to click the plot and type, G to turn on grids, L to turn on, logarithmic scale and things like that is really nice. Okay, so then it's also important for debugging. So I'm going to run the same piece of code, debug for me in this code, in this IPython prompt, and my window pops up because I made a plot, but I have a problem here. So it says, key error deck J2000, and I can look. So now I'm not in the debugger right now. I could type things right now. I could look at the variables that are in the global scope right now, and it would be fine. But the variables I want to look at are in a function call. So how would I look in those? Well, I go reset debug. Now I can go up U again to the upper. So now I was in some deep inside table.py. I go up one more. I'm in still in table.py get item somewhere. I can see what item I'm trying to get here. Just J2000. You can look at self.column, which is one of the variables there. You can see all the columns that are here. And actually, here I might notice, okay, that isn't the correct one, but what is the correct one? I say, oh yeah, there's one called DEJ2000. I probably just made a typo. If I wanted to keep going up, I could see here's now where in my code now, where I was actually calling that. So I was calling this function on line 33. I said table deck J2000 to 2 degrees, and that was the wrong key. Okay, so I quit. And now let's fix that. So I'll just open to my editor this debug .py really quickly, and I will change it says deck 2000 to DEJ 2000. Let's see if I have any other bugs in this now. If I run debug for me, actually don't remember. Yeah, so now my code works, and now it's fully interactive, right? So I was able to go in and spin both the plots. So again, it's a bit of a contrived example. Usually you have much more complicated errors than that, or ones that you can't, but in the debugger's useful word, you can't figure out what the actual error is. I probably could have guessed it from the error message. So the other thing, so now that it's working, if you're just curious to see how the code actually runs, you could just run that piece of code in the debugger directly. So, well, there's a couple things you could do. You could do, let's see what time we're right now, just make sure I'm not going too far. Okay, perfect. You could do, well, let's do a few things first. Let's edit this code again, but then in some part of the code, like let's say when we're getting, let's say maybe when we're making the values. Is that an interesting place to stop? Or no, let's okay. This is a function that's called deep inside the code. So let's say I want to see what's happening. I think I'm curious what this is doing. Let's put a breakpoint here. So I just say breakpoint. Now when I run the code, even if it's not running in, by the way, in IPython, this could be in regular Python as well. Now notice I've jumped into a prompt called PDB, and it has this arrow saying I'm at this line. So this is this you are here line again. If you type L, it gives you the listing. So if you want to see a bit more of where you were. So I'm in this function, convert gal to deck. I haven't executed this function yet. So if I typed lon right now, it would say not defined, but I have defined coordinate and G coordinate. So if I type coordinate, you see, okay, that was an array of coordinates. Galactic coordinates is an array of galactic coordinates. So you can inspect the code here. And then let's say I would say, okay, well, that all looks good. Let's go to the next line. I want to go now to execute this one and go to this next line, lat equals 2 degrees. So I type N for next. Now I'm at that line. So if you see the listing again, so I was at line 68, now I'm at line 69. Now if I type lon, it's available. By the way, I'm typing the commands directly here because I said you can type any Python expression. That's not entirely true because there's all these keywords that are part of the debugger. Of course, if you have a variable called display or something like that and you type display, it's going to not to print the variable. So you can always type well, there's two things you can do. You can use the Python print command, so you can type print lat or lon, or there's a help shorter debugging command, just p. If you do p lon, you don't need any parentheses. That also prints a variable, and that's true in the C debugger as well. Okay, so what other things can we do here? Well, so let's say we want to, first of all, let's see where we are. Let's type bt backtrace. It shows the entire call stack going all the way up to the starting Python, but you can see that we're in this convert to gal, and that was called by, actually that was called by the outermost scope of the program, so you don't see anything particularly interesting here. This is all the others. But let's say if you were deep inside a function call, you'd see all the function calls on top of there. But what I wanted to show is, first of all, what happens if you step into a function. So what happens when this line gets executed, but we want to see what's actually happening when .value gets called, or where to gets called. So if you type I to go into that function, S to step into the function, we now have jumped into sky coordinate.py inside astropy, and we're actually inside the getAttr function of that. If we do a longer listing, you can see what that function does. And then we could actually, if we wanted to, step through that code and keep stepping to each line, next line, and actually look at what's actually happening. So here we're at a line called, that says, if not, attr starts with underscore and has attr this, return something. So this is some very complicated function. I don't know what it's doing, but I can print out any of the variables here. So if I want to know what self.sky coordinate frame is, I could print that, and I'd see that that's a galactic coordinate frame. So anyway, I can go back. Now I want to keep going to the next line. I'm a bit stuck here because it would, if I hit next, I'll go through every single line of this function. What I could do is, if I'd set the breakpoint somewhere outside of a loop, I could type continue. That will finish running my program, by the way, so the program finishes until it gets to the next breakpoint or until the program ends. So that got me back to the end of the program. So now the program's completed and I'm not in the debugger anymore, but I'm back into IPython. I could show you, so okay, the next, let's go back to the slides for a second. So I have a couple more, if I can find the slides, where did they go? I actually don't know what that is. Let's click my, there. So, okay, that was the command line debugging and debugging in a notebook, but that's kind of tedious, as you noticed. You have to remember these commands and you have to kind of think about where you are in the code. So what I generally recommend is using a GUI debugger, although it's a bit sometimes harder to get going, or you have to be using the right IDE for this. But so for the example I'm showing here is from PyCharm, but it's true of basically all GUI debuggers. So generally in a GUI debugger, you have some little bar. Actually, in fact, I believe I have a, yeah, let me go back here. Okay, yeah, you have a place where you can click in the margin next to the code, and you can say create a breakpoint there. So that makes usually a little red mark or a stop sign sometimes. And that tells me that when I run the debugger, I want to stop at this line and go into the debugger at that point. And you can have many breakpoints, by the way. I didn't mention this, but in the text mode, you can also, there's a breakpoint command. You can add breakpoints into your code from the debugger interface, the command line interface, as long as you know the line number and the name of the file. It's a bit tedious. So I think doing it this way is much preferred. Then what you have to do is configure your GUI to go into debug mode. So usually you have to open the, right click on the executable part of your script and choose debug, or sometimes there's a button, like here actually, I think it's pointing to the wrong place, but there's a little button, that's a little bug here. And if you click that bug, that would start a debugger, but you may have to sometimes first create a debugging config. I'll show you what that means. But that just makes you have to tell the debugger what program to run, because in a editor like this, it doesn't know which file you really want to run as the main file, right? It knows that you have a file open, but doesn't know which is the main file. So you have to tell it that. But once you click the debugger, basically what happens is you jump into debugging mode, and it looks just like your IDE normally, but usually you get a pop-up. So in PyCharm, you get this bottom pop-up here that shows the stack frame, the current variables, and it highlights the line that you're currently at. So this is this you are here line that I was talking about before. And you also notice that code that's already executed, the values of that code actually appear next to the line of code. So that's super useful. So even you have to do anything, you can just sort of look, I'm here in the variables that have already been executed, I see what the value is. So that's super helpful. if you put your mouse over any executed variable, it'll also pop up details of that. So it'll look something like this usually. So it lets you drill very, very deep down into all the, so you can look inside a variable if it's a variable that has, so this is an example from the code I've been working on for analyzing shrink-off telescope data, and I'm looking at a particular event in that data, and it's smart enough to be able to drill down into my complex data structure, and I can look at the sub parts of that data structure and the values of all of them, and even things like if they have a repr method, which I don't know if you talked about that last week, but it'll even print that, so you can actually see very detailed information about the data structure as you go into the debugger here. So that's much better than what you get from a print statement, right? You couldn't see all that information. Here you can really go deep inside. The other thing you can do with PyCharm, and I'll show with other ones, you can view, let's say I wanted to view one of the arrays that are in this, so a NumPy array, you can view it as a two-dimensional plot. So this is the data view. Sorry, I'm probably right in front of this, but you can see basically the bottom here. So this is the values, and it's color coded by the brightness or the the intensity of that value compared to the other ones. So all debuggers look kind of like that. They usually have code, output, the stack somewhere, local variables, global variables. Sometimes those are combined. And then you have a place to put breakpoints and to show where the current line is. So once you understand that concept, all debuggers work the same way. Again, this is that C++ or C actually, not C++, C debugger, GNU debugger. And this is the one that has one extra feature, which I've never found actually in any of the Python debuggers, but you don't really need it mostly in Python. Just being able to drill down, like I showed before, into data structures is enough. But this lets you actually create graphical views of your data. And this is particularly useful if you're writing C code that has pointers, because pointers are always complicated to think about. It will actually show the pointer and where it points and what it points to and things like that. And it's quite nice. So there's lots of types of debuggers, but they all look, this is from, I think DDD was written probably in the 90s, and it looks basically the same, right? It has the code, it has some output, it has a way to look at the stack, and it has some other information. You have the same buttons, step into, next, continue, interrupt, etc. Just for completeness, this is what the debugger looks like in VS Code. Again, the same, almost slightly differently layout than the PyCharm, but almost the same. You have the call stack, you have the variables, you have your breakpoints, you have the currently executing line, you have the buttons to either step into, step over, or lines. So rather than typing commands, you type buttons. This one I don't think I mentioned. If I go back here, the buttons to move through the code are on the left and up at the top here in PyCharm. We'll show a demo of that in a second though. And then this is Emacs using DAP mode, and actually DAP mode uses the same debugger as VS Code. So it looks sort of similar, you even have the same toolbar and a kind of similar layout. So, and I think any editor you have, if you use VI or Vim, there's debug plugins for that as well, and they'll look basically the same. So let's do a quick demo of that. And I think we're actually right at the end of the time for this lecture. So it's perfect. And just for completeness, I'm going to open up, I think I already have it open. Yeah, so I have PyCharm open here. And this is actually running some code that I've been working on. So this is actually real code that I'm trying to debug in Profile later on. So this is real work, just to show you. It's not a very complicated example, but this is actually calling an enormous amount of code behind it. So it's basically looping over a bunch of events, which are basically images of shrink-off showers in our camera, calibrating them, processing them in various ways, then writing out the results to a disk. And it looks very, very simple, but actually what's going on behind all of these is very complicated. And so what I often like to do is be able to say, okay, now something's going wrong at one of these steps. I want to go deep inside and see what's happening. So what I would do is I would create a breakpoint first. So I'd just click in the margin and you say I created a breakpoint. I can create other breakpoints too. I can create as many as I want. So it'll stop at each one of these. So actually, let's try that first. Let's put one there and one here. Then what I usually have to do is right-click on your piece of code and click debug that code. And that will actually, in PyCharm, that will both create a debugging config and start the debugger. Once you create the debugging config, you can just click the debug button at the top but otherwise it doesn't know which file to run. So let's do it this way. So run debug, and see now it's starting up the code. It says connected to debugger. Let's think a moment. So it always takes a few seconds to start up, probably. Let's hope this actually demo works. It worked when I tried it earlier. Okay, in fact, maybe I have to start push. No, there it is. I just had to wait a bit. So now, okay, it's run, and you see this line has turned green. So it actually ran all the code up to my first breakpoint, and the breakpoint is now green. So it hasn't run yet, the breakpoint line yet. And you can see already I have the output of variable. So I have the file name is this file name here. I have it's printed out. It's the values of some of these objects that I've defined. And down here, I have all the memory, so I can actually look into any of those and look deep into what all the variables that are inside them. So some of these are classes. I look at the variables inside those classes. Great. So let's move. Oh, and if I put the mouse over something, you can see also that. And if you click the little plus here, you can go deep inside that object. So that calib is an object that has a bunch of function calls, and these are actually variables that are inside it. And you can really look inside all those variables if you want. So let's go to the next breakpoint. So to go to the next breakpoint, I just want to click the continue button. So resume program, and then let's see, something should happen. It's not happening. What happened? Resume. Oh, yeah. Okay. So yeah, because it hit this twice. So now I'm at this breakpoint, and I've already run this calib function, and I can look at my data if I want. So this is a huge data structure, and there's all kinds of data inside it. For instance, I know that because I know how this looks, there's a piece of data inside here for each telescope identified by number that has a waveform array in it. This is basically a two-dimensional array, or maybe a one-dimensional array in this case. And if I click view as array, it'll pop up. For some reason, actually, this doesn't always work. Sometimes you have to type the entire thing in here, but I can type. Telescope was that? 8. Let's see, that's not very telescope. Let's see which number was actually there. Here we are. Okay, so there's one called 13. All right, so this is a valid variable in that function. Okay, now I'm displaying the variable as an array. So what I see here is actually the value of each element of that array. They're all fairly similar. In this case, because this is basically a blank image that I'm looking at, there might be some data in it. If I search through it somewhere, there's probably some bit of data. But yeah, so it's really nice to be able to quickly look at values and see, okay, I don't have any crazy, there's no numbers or other crazy values that might be in there, right? Let's see, anyway, so that's how that works. Then if I wanted to step over this and go into the next function, for instance, like I have these buttons here, so I can say step over. So now I go to the now I'm at this line, process shower, but let's step into process shower to see what it, step into my code, you can step into other code. So now I'm in this completely other function. Step into that as well, because it's calling this another function. And you can really go deep down inside all the function calls that you wrote and go very, very deep inside them and see all of the variables that are currently running. So here I'm down 3 levels into it. You can see this is the call stack, or I'm down 3 levels into this call stack. I can go to the next line. Let's see, step over. Step over, step over, step over, step over. Now this variable is now set, or no, it's probably not. Let's see. So that I happen to pick one that didn't do anything useful. Let's see. I can get to a line. Okay, so here I've stepped over this line. Now the line has a value now. So this variable now has a value. So it's super useful. I didn't have to write a single print statement. I can see everything that's happening. I can pop back up the stack, by the way. So I'm still executing at this point the function, but I can see where that function was called, where that function was called, where that function was called. So I'm back up here in process, but actually inside there. And then when you're done, you just push stop. So that's a GUI debugger. Okay, so that's the end of this section. The next topic, and I don't think we have a break right now, right? Is that correct? We go to the next immediately, is profiling. And then at the end of this, we'll have some time to try yourself some of these. So profiling is the next topic. Let's make this full screen. I hope that's now visible and my slides are changing. Are my slides changing? Can anyone tell me?
Yes.
Okay, good. So first of all, what is profiling? It's there's another way of inspecting your code. So it's not like debugging, but it's a more high level way of inspecting your code in such a way that you can see where resources are being used by the program. So for instance, CPU resources, so computation time, memory resources, and also which functions are being called and how often those functions are being called. So if you have 3 functions and you run your code, maybe function A is called 1,000 times, function B is called 1 time, and function C is called 12 times, something like that. This will tell you that. So it also helps you debug problems in your code like memory leaks, and that's where you've allocated memory, not removed it for some reason, which can happen in Python, by the way, even though it's done kind of in an implicit way, as long as you by mistake kept pointers to that or references to that memory somewhere. And also lets you identify hotspots in your code that might be useful to optimize. So things that will be that in the next after the break we'll talk about optimization, and this is how you find the places of your code that you want to optimize. So the simplest method of profiling is with time it. I think you've already seen this, so I'm not going to go into extreme detail here. I'll show an example of it in a moment. But I just want to point out that why wouldn't you just write? I've seen that people doing this all the time, by the way. They import time, they do start equals time that now, they run some code, they do stop equals time that now, and they print stop minus start. That's great, but it doesn't really measure what you want to measure. That's measuring what's called wall clock time. So it means it's measuring what's happening in real time, but your computer might be doing lots of other stuff in the background. It's running Zoom, it's doing all kinds of things. And so what you really want is the CPU time specifically for your process. And you also want to do this many, many times to get a good statistics for it. So that's why time it is really important. I think you really should use time it and not this. And even if you're running in a regular piece of code, you can import time it as a module. So in regular Python, you can't type %time it. That's only a Jupyter Notebook command or IPython command. But you can import it as a library and run the same options from regular Python code. A second way to do this, and we're going to go to demos in these in just a second, this is just an overview, is to use a real profiler. And a profiler is a bit like the debugger. So in the debugger, as I said, in debugging Python code, you can put in print statements to see what the values are, or you can run a debugger and it shows you all the variables. That's the same concept here. A profiler basically runs time it essentially on every single line of code and tells you all of the information of, or every function in your code, not every line, although there is a version for lines. I'll show that in a second. Python provides actually a few different profilers, but I think the one that you should always use is the one called C-profile, because it's the fastest and fairly easy to use. If you're using C++ or C, there's one called gprof, by the way, that does exactly the same thing. So the way you run it is you run your script in a special way. So first you type python-m cprofile, that means load the cprofile module, give it the option -o output, and you can call it whatever you want here. So my script.pstats, and then the name of your script. And then that will run the script as normal. It'll seem to run normally, but actually at the same time, it will generate this database of statistics information about every function call. And that's a binary file that you have to look at in a special way. There is actually a package called pstats. If you do python-m pstats and then open this file with that, it gives you kind of an ugly command line interface to do it. I'll show you that in a second, but it's not really the best way to look at it because it's a bit clunky. But fortunately, there's a really nice command built into Anaconda, or comes with an Anaconda Python distribution called snakeviz. And if you type snakeviz in the output, you get this beautiful, like a flame graph style thing that shows you this is the stack frame now going the other direction. So this is the outermost scope, and the lower, deeper and deeper function calls go down here. And the width of these is proportional to the amount of time spent in that function. So I ran actually this on that same little bit of code that I've been working on that I showed you in the GUI debugger. And I could see that this is actually something we're really doing right now for real work, is to see where the speed bottlenecks in this piece of code. And I can see the parts that take the most amount of code. And I found that, okay, Hillis parameters, which is one of the functions we call, takes a lot of time. And if I looked deeper in here, I found that it's well, in fact, I can show you this as a demo. Before explaining this, let's just do this as a real demo. So let me move again to my my terminal here. So this is a demo not of code that you have. This is again of real code. But I'm going to just try it and see what happens. So what I want to do is run my code. So I have this code in here, and it's a bit bigger so you can see it. And what I do want to do is Python -mc profile -o. I'll call it simple pstats, and then my code is called simple pipeline.py. I think that's all I need. So I'm going to run my code. And it takes a second to start up. It adds a little bit of overhead when you run, so things run a little bit slower than they would normally, but not by much, because it's collecting statistics at the same time. So this code takes a bit of time to run. It's computing some information. It should only take a few seconds, hopefully, unless I did something wrong. And then one thing to point out when you do profiling, you generally want to profile code that takes a little while to run. If it runs too quickly, you won't get much. The resolution of the time will be a bit too small. So you want to run on a larger data sample or something. So here I ran with 100 or so events. Okay, so if I ls what's here, so what I got at the end is my output for my code. That's what it outputs. But I also got the simple.pstats file. And if you look at that, it's just data. It's some binary data that's not normally visible. However, if I type snakeviz, simple.pstats, it will open up your browser. Let's see where it's doing. Okay, yeah, it's to open the browser in a window. I hope you can see my browser. And you'll notice it's loading some stuff here. This is actually such a complicated program. It has so many subprograms that it's going to take a while to load everything. So it's actually, you can go here to cutoff and say cutoff 100, and it'll be much faster. Okay, so now it's loaded faster, but it won't go down as deep into the call stack. So it showed that I ran the program. Here's my code that I ran. By the way, you can see these other little blocks here, which are actually, if you look on the right, it's a bit hard to see. So on the left here, it shows you what is being, I can make this larger. It's a bit small. On the left, it shows you when the mouse is over what function was actually being run in detail. And so I can go back here. And so at the same level as pipeline, as my simple pipeline.py, there's all these other blocks here. And these are actually Python itself loading up. So it's init.py and loading up various dependency files and things like that. So this is all just Python overhead of when it has to load up all the shared libraries. Then it runs my main program here. So I can, if you click it, it'll then put that part of the stack frame at the top, and you see the detail below. In my main program, I have, let's see, at the first level of call stack, I have 1, 2, 3, 4, 5 things that take up most of the time. And you can see the one that takes the largest amount of time, 12.7 sections, is this shower processor.call function. This one is actually the IO, so reading the data takes up 9.2 seconds of my code. And the rest are things like, let's see, this is on the left, it shows calibration. No, that's still, yeah, no, so writing the data, reading the data, and processing images and calibrating. So those take very little amount of time. Most of the time is taken in these. So now I know, okay, these functions are fairly optimized. This one probably needs some optimization. And what I can do is drill down into it, just like I did in the debugger. I can click, go deeper into its hierarchy and see which of the parts that actually, so each one of these these things is a function call, by the way. And I can see which functions take the longest. So I see that sky coordinate transform to is the slowest thing probably. So that's a astropy function. So most of my time is spent converting sky coordinates to other sky coordinates in this code. And so if I speed that up somehow, I don't need to touch the rest of my code. I can just make a faster coordinate transform maybe, and I will save most of the code. I don't have to even look at the other parts of code. So this is very useful. In that, if I want to see what's slow inside that, I could click that, go deeper into that. Now I'm looking at that, the sky coordinate transform. This is all, by the way, now in astropy. So this is all astropy stuff. I can see where astropy has gone wrong. Actually, is this actually totally strpy? We have some custom code that uses strpy, so it may be our fault as well. Let's see. But anyway, you can still drill down and see that it's actually this transformation call function that takes the longest time. If I look at that, you can see where it's using its time, and then finally you can find basically where the speed bottlenecks are, right? So it looks like realize frame is taking up a lot of the time here, for instance. So this is how this works. If you click the top one, it goes back up the stack, or it moves you one element outside the stack each time. It's going to be a bit slow here because I have so many depths. Or you can click reset zoom to go to the beginning again. You can also view it as a starburst like this, which is sometimes kind of nicer for visualization, but I find since it doesn't print the names on them, you have to always look to the left to see which each one is, so it's not quite as useful. And what you might see here is below is you have a little table of all the functions in the every function being called. This is why this is so slow, because this is a complicated piece of code and there are literally hundreds of thousands of function calls. You can sort this table by clicking here, like sort by total time, which is already sorted by. And you can see which functions. You have some weird functions here that are actually part of built-in parts of Python, so they don't mean anything. Like FFI, well, some of these base.py, things like that are probably not, I don't know, those are probably part of the quantity support of strpy. You can also sort by per call, so which function is called the most, not necessarily takes the most time, but which one is called the most, and by cumulative time, and the amount of time per call. So these are different ways of here, of course, so it's interesting to see. You can really see so that's the non-graphical view of the data, basically the table view. And you can search by function call here as well. Okay, so that's let me close this here. That is SnakeViz. Let's go back. Where was I here? Let's close SnakeViz. So it basically runs its own little web server, so you have to Control C to get out of it. And let me go back to my slides if I can find everything. They always disappear. But yeah. Okay, so that's really the way I recommend working. So again, remember, so the way this works is you run Python just with this. All you have to do is add this extra little bit of command to your Python command. This also works in IPython. Python doesn't matter. Run your script and then run SnakeViz, and you can identify bottlenecks. There's other ways of viewing the stats, so SnakeViz isn't the only one. There's a much more fancy one that's sometimes useful that I use occasionally called QCacheGrind, and it's part of the KDE project, I think, originally, but it runs on macOS as well without any problem. You can install it with Homebrew if you're on a Mac, brew install QCacheGrind, or if you're on Linux, apt or yum or whatever you use to install, QCacheGrind works. Windows, I'm not sure. There's probably a version of it you can download. I haven't tried it. Maybe you can even get it with Winget, I'm not sure. And then you have to actually convert the output, this pstats output, into a different format for it to load it, but that's quite easy. You can install this function called pyprof to call tree, run it on your output.pstats, and actually it'll automatically, just this conversion will also open the GUI for you. See that this GUI will pop up, and here you see something a little bit like SnakeViz, but even more complicated. It basically shows all your function calls and time spent to them and sub-functions, and you can drill down into it. You also see a tree view of your code at each step, and the same kind of table view that you can search and sort. And it's just another way of doing it if you don't want to use a web browser. And SnakeViz, this has a few more fancy features. And there's others as well. So, and by the way, these I haven't tried SnakeViz, but in principle, the output format of this is the same as the output format for gprof, for C++ and other code. So in principle, you can also look at code that's not Python in these. Certainly with QCacheGrind you can, I think also with SnakeViz, but I haven't tried it. There's a couple other ways you can do profiling. So here we're going to show this in a demo in a second. Inside a notebook, there's actually a magic function, a bit like timeit, called prun, that will profile the current cell and pop up a sub window with a table in it that has the information like what we saw before. I'll show that in a second. Then there's the question of what happens with, okay, now you've identified a particular function that's very slow. But in that function, which line of the function is actually the slowest line is the next question you might ask yourself. And there's an answer to that. And you can install this code line profiler using Conda. And I think if you updated your environment, I don't know if my pull request was merged in yet, but if you update your environment from the school to what's there now, you'll get this automatically, but you can also just type it or Mamba install, whatever you want. And then the way it works is it's slightly different. So it doesn't just profile every single line in your code, because that would be prohibitively slow. So what you have to do is put the word @profile. You have to edit your code, put the word @profile, so a decorator, in front of any function that you want to profile. Then you run, well, there's two ways to run. There's this command kernprof, and then you dash, I think that's an L if I remember right, and then script to that you want to profile. Or is that an I? I have to check. That should use a font that's more, we'll demo this in a moment. And this will generate an output file called script-to-profile.lprof, which is a line profiler database. And then you can use this command python-m line profiler, that lprof file, and then it will display all the lines in the code and also show you how long that line took to run. It'll show all the lines that had the @profile in front of them. Again, you can do that in a notebook. So there's a special notebook extension for line profiler that you get if you install line profiler. You can then run in a cell this lp run command. It's a little bit confusing as well. So you have to do -f. You can have any number of these -f options as you want. So it's the same as putting you don't have to put the decorator @profile in front of your functions. You just put which functions you want to analyze here. So let's say I have 3 functions, func1, func2, func3. I would put -f func1, -f func2, -f func3. Then I have to run a Python statement that somehow calls that bit of code. So like a main function or any other function that calls those functions. If those functions aren't called, obviously it can't profile them. So it needs a way to run them. So for instance, you could just say, I want to decorate my func and call my func itself with some options, or you could say decorate my func and call some other main function that calls my func, and it would still work. So for more realistic examples. And this will again just give the same output as running it on the command line, but in the notebook, and I'll show that in a second. The third thing to do is that now you know where the speed problems are, you might want to know where memory problems are. So sometimes your code is using way too much memory and you want to know why. And there's a few different ways you can do this, and it's not such a simple, because of the way Python memory management works, it's a bit hard to debug than other things. But if you install the memory profiler, which again is in the environment, and then you run your Python script with this command mprof run, then type mprof plot, it will actually show the memory usage as a function of time as that program was running. And I'm going to again demo this in a second. But I wanted to show this overview first. And then it'll tell you also where the peak memory was used. So in this is an example I ran a while ago, and the peak memory was after 90 seconds or so. And then it flattened out pretty much, and then it closed and things went down. Just like line profiler, the memory profiler also has a line profiling option. And it works exactly the same. You run python-m profiler script, and you have to decorate with @profile any piece of code that you want to measure, any function that you want to measure. Then that function, you'll get a line-by-line output, and it will tell you, let's see if I put the wrong, I think I put the wrong output here anyway, which is, it should show not the time, but the memory used for each line. I pasted the wrong graphic in here now that I see it. But basically it looks the same as the line profiler output. You can do the same again in a notebook. So there's magic commands memit. Now it's a little bit confusing. This is something I really had to think through quite a bit, and it doesn't always work consistently. And that's because in a notebook, you have all these variables loaded, and there's Python, keeps all variables in memory and garbage collects, meaning it deletes memory only certain times when it needs to. So when you're running things sort of non-sequentially in a notebook, it can get very confusing. If you run the cell multiple times, you might not get the same result, because what you see is actually total memory used, not necessarily memory by the exact line of code that you're running, because that's just a artifact of how Python runs. So there's two options. There's memit and MP run, which lets you do a more detailed version. And memit just runs a single statement. And for instance, here I tried range 10,000, which should be a generator, which should basically use no memory whatsoever. And what you see is that the amount of memory if my current notebook was 89 megabytes, but the increment from before this line was run is 0. So that means really this range function took 0 time or 0 memory. Using np.a range 100,000, NumPy had to allocate this 100,000 array elements. And so the increment now is 0.52 megabytes. So you can see this line took memory, this one did not. But if I rerun this again, you might get a slightly different result because now this memory is still allocated. So this one is, it can be quite confusing to interpret, but it does work. Okay, then let me just see if I want to come back to, yeah, well, I'll do the demo after this. So I'll say one more thing is that using these memory profilers, you actually have an option to jump into the debugger at a certain amount of memory allocation when a certain amount of memory allocation happens. So that's super useful. So you don't need to say, well, something is allocating, a gigabyte of memory in my code, and I don't know where it's doing it. I can say, well, run the memory profiler, set my PDB memory threshold to, here it's 100. I think this is in bytes or 100. Oh no, it's megabytes, I guess. So let's say 1,000 if I want to see where a gigabyte was being allocated. Run my script, and then the script will actually jump into debugger as soon as something allocates a gigabyte of memory. So it's very useful for debugging where memory is being lost. There's other ways you can, by the way, there's many other ways you can profile memory. There's this memory usage thing you can import that during your program running. You can even print out the memory usage if you want as like a log, which is sometimes useful. But let's do a little demo of this. So let's go to the notebook again. I'm gonna open my profiling hands-on here. Let's see, I'll make this full screen. And I can close this, make this a bit easier to see. Okay, so here I'm importing just some things I need. I already have memory profile and line profiler installed, but if you need to, you can install them with Mamba. And here what I've done is, well, first is a simple question. Like this is something that you do pretty often is, which implementation is faster? See, I have a function, I've implemented it 2 different ways. Which one is the quick one? So here I make a really simple demo. I have a function which allocates an array, mij, which is sine I cosine 0.1j. So it's just some initial condition for a bit of, I don't know, some analysis I'm going to do later. And I implemented it 3 ways: with a for loop, with an array, and with NumPy. And what I want to do is just use timeit. First of all, let's plot them. So the arrays all look the same. So this is the plot of each of those arrays. That's good. So they all do the same thing. And then we're going to use timeit to check the speed of each one. Now here's a little trick that you might not know. So you already have seen timeit, so I'm not going to go into the details of that, but timeit has an option called -o right here. And if you put timeit -o, you can actually assign the results to a variable. So it's a bit weird looking. This is not Python really code. This is because this is all a notebook extension. There's not usually dashes in Python code, but so I can run my code in the loop, my code with a list, my code with NumPy. Let's let those run. And okay, so they've each run. And then because I've collected those results, I can make a little plot performance function that just takes the mean and the average, makes an error bar plot. And then let's plot it. So this is what I usually do to compare things. So I can see, okay, the loop version took, and by the way, I plotted this in no, this is a linear scale, right? So loop version took, I don't know, 6 × 10⁻⁵ seconds. The list version was a factor of maybe 2 faster. The NumPy version was much faster, right? So you can immediately see that NumPy was the best way to do this kind of array operation. The same thing you might want to do is, okay, now having that array, which is the fastest way that I could make the mean of that array. So I could either, sum the array using the Python built-in sum function, then divide by the size, or I could just call numpy.mean, or I could call even numpy.mean of a versus a times dot mean, which is slightly different in NumPy. So I did all three of those and plotted the performance. And of course, time it because it runs each function hundreds sometimes of times, or tens to hundreds of times. Okay, in this case, 7 times 10,000 loops. To get statistics, it takes a little bit of time. And I see that numpy a.mean is faster than numpy mean of a, which is faster than by far than sum of a. And that's something you might not expect, that NumPy has 2 ways of calculating the mean, and in fact, one slightly faster than the other. So that's interesting, right? So now using a profiler to do that instead, so that was with timeit. Let's imagine you have, okay, here I made a contrived example of it, 2 functions, slow function, which just sleeps for a second and then returns x squared, and a faster function, which returns x squared without doing any sleep. So this is a completely contrived example. But let's say I have those 2 and I have a bit of code that loops over a range and calls those the slow function and then the faster function. I can run it with this --p run option. And what I get is the output here. And you can see that slow function took a cumulative time of 5 seconds. Faster function took 0 seconds in this case. It was so fast that it couldn't measure, within precision the answer. You can actually get, this returns a stats function. That's why the minus r is in there. It'll return the function like timeit does. So I just have to capture that using the underscore. And then I can also sort those stats by, let's say, number of calls or per call instead of by cumulative time or something like that. So you can play with this table or get the information out of it or plot it or something. Not quite as nice as using SnakeViz. I think SnakeViz is better, but you can't use SnakeViz inside the notebook very easily. So for line profiling, let's do the same thing. I said you could load the line profiler from an extension. So you actually have to type this first, load extension line profiler. Then again, here's my same function that does 5 iterations and calls my slow and fast function. So I did LP run. I told it I want to profile the run all function, and I want to call the run all function. And here we see the same thing. We see that the code, the slower function clearly takes much more time than this one. So this is a bit of a, these examples look very similar, but in fact, they're doing very different things. So this is telling me per function which one, and this is telling me per line. It just happens to me I have 1 function per line. So, but if I had some other, let's say, well, you can see one difference you can see is that the for loop here. So it included the for loop as something to profile. So that normally isn't a function call. It's just part of the for loop, and you can see how much time it took, computing range and things like that. If you wanted to see inside, let's say slow function here, you could also put -f slow function, run all. Now it's, we have 2 -fs. We're checking run all and slow function. And you see inside slow function now, most of the time is taken, as we'd expect, in the sleep. So time.sleep takes a huge amount of time. Return x squared takes very little amount of time. So this lets you, again, drill down and see where your code is being slow. Okay, so we have about, 10 minutes left. So let me do a couple more demos then. So I also ran the same, that create array loop function that was above before. So that was this function that made that 2-dimensional array. And ran it in the line profiler, and you can see where, so that was this loop here, and you can see where the time was spent. So most of the time, as expected, is spent in this for x in range n, because that's called very often. It's the inner loop. And of course, row.append is where all the time is spent, and especially in the inner loop version of it. And so that can give you an idea of where something's going wrong. So the same thing for memory profiling. Let's import loadx to memory profiler. And then let's try, this is the same example I showed in the notebook, running memit on np.sum of some let's say calculation, or mem it on sum of using the Python sum, not numpy.sum of a generator expression. And you can see the total memory is the same because that's the total memory of my notebook. But this one took 30 megabytes. This took 0 megabytes. That's because range and sum both are generator functions in Python, and so they only operate one element at a time and then compute the sum. So they don't allocate all the memory first, and so they use basically no memory. So that's interesting. You can use this to compare different ways of memory usage versus implementation. Now, of course, we learned earlier that this is much faster than this one, so it's not always good to minimize memory usage. You sometimes, using some memory, you gain speed. So another thing you can do here, what I'm going to use, by the way, this special command write file. That means take everything inside this cell of the notebook and write it to a file called temp sum. That way I can run it externally. And the reason why I'm doing this is that I want to try this mp run command, which is this sort of fancier version of memit. That's the same thing you'd run from the command line using this kernprof command. And you can't run mp run on code that is in a notebook cell. It has to be written to a file. So it has to be a library file that's imported. So it has to be something that has an import statement here. So that's something to keep in mind. If you try to run this on one of the functions that ran above, it'll just crash and say you can't do it with some cryptic error, but that's why. And that's in the documentation. So import that function now. So I wrote it to a file, I imported it now. So I'm not, actually, this is not executing a cell. This is writing it to a file, importing that file, and then I run mp run on it. And I give it some large inputs of 500,000, so that it takes some time to do the calculation. And let's see how long this takes. And basically, this is the same two things I profiled up here with memit. And like the regular profiler, rather than having to explicitly put each statement in, this will do the profile on every statement. And so if I had 100 lines here, it would do all 100 lines. Or 100 function calls, let's say. Yeah, so now I have the output here. It says, okay, all the memory is being allocated here, 7.7 megabytes. And the total memory is 135 megabytes, and there's basically 0 allocations in these two lines here. Okay. Sorry, I need to go back to my notebook. Okay, so that's all I had for optimization and parallelization. I think we're basically a few minutes early. So are there, I know that was a whirlwind of information, but if there's a few minutes of questions, we can do that as well. And then we'll go to a coffee break.
Thanks a lot, Carl, for this detailed overview. So we've watched the Slack channel, and I think there are some people, when doing the exercise in the notebook, I think received somehow a dying kernel because of the recursion, but like I think increasing the recursion limit interpreter seemed to resolve the issue.
Oh, that's interesting. So maybe it read on his memory or something on their machine.
Good.
Yeah, basically you should avoid infinite recursion because that means infinite amount of memory is being allocated. So I mean, it's not strange that the kernel died actually.
Okay, then there was another question, which I think is probably an interesting one in general. So if we do Python -MC profile, or probably just profiling in general, want the profiling add extra running time to your script, or is like the extra running time in general negligible?
It's a small amount of extra running time. Yeah, it does. So because it's collecting statistics and writing out information, so your script will run slower. It's not massively slower, though, I have to say, at least not for any of the programs that I've run. But you do notice if you measure wall clock time, it will be slower. So you don't want to run that every time. It's only when you want to profile your code, because of course it also writes out a large database file, which takes up a lot of space on disk probably. So yeah, it's something you run once in a while, not every time.
In general, would you say there are situations where this matters, or basically doesn't it matter at all, because typically you're comparing, for example, implementations and they have the same overhead anytime?
Do you mean it doesn't matter whether you run profiling or not, or
no, just in general, like this additional overhead introduced by profiling, does it matter to you somehow in a measurement? I mean, because typically, for example, you're looking at relative numbers to compare.
Yeah, no. Well, in fact, it takes into account the overhead. So it doesn't. The overhead is not included in the results, if that makes sense. So the results you get are not polluted by so for you on the wall clock, it takes a bit longer to run the code when you have the profiler turned on, because of course it's doing the profiling, but its results do not include the profiling itself, if that makes sense. So it really only includes the execution of the actual code. So it's careful to not increase the running time of your function, but the running time of your whole code, because in between functions, it's doing some profiling things, will increase, if that makes sense. So that's why I say you wouldn't always turn the profiler on every time you run. If you're running, your analysis, you don't turn profiling on. Only profile it when you want to do it. But the results it gives are as if you didn't have profiling turned on, and how long it would take. So it's taken into account.
Okay, thanks a lot. I think that's basically it for the question. I mean, I can add just one more question from my side. So have you heard about a tool called PS Record? And have you used it?
Sorry, what was it called?
PS Record.
Is this the one that was mentioned, I think, in the Slack last week from, it might have been that. I think somebody typed something about it. No, I hadn't actually heard about it, but I guess it's like a bit like mprof that tracks the amount of memory and CPU every few seconds or something. Is that right?
Yeah, I think that's basically what it does. I think internally it probably still relies on C profile. I don't really know. I've used it before, but it's just like I think a very nice or simple API for debugging and profiling.
Yeah, I didn't mention that there's actually two types of profiling. So that the sampling profiling, and that's what that is a sampler. So basically it takes snapshots every n seconds or every few milliseconds or whatever, and records how much memory your whole program is being used. And then a profiler like C profiler is a function call profiler, which checks every time a function is called. So it's not in time, it's by function call. So they work slightly differently, but the results in the end, are not so different. I think you get less detailed information with the sampling profiler, but it's easier to use. You just basically run it and it gives you an output. In mprof, I think it's a sampling profiler, whereas the line profiler and the ones profiling speed are like C profile is a function call profiler.
Okay, thanks a lot for the clarification. Then I think we close the session on debugging and profiling, and then we're gonna have now half an hour of coffee break, and then at 11 we're gonna be back with the code optimization.
All right, see you then in half an hour.